So now let's work a little bit closer to our goal of analyzing oscillating systems, which come out of this second order differential equation. So we'll do the simplest second order linear constant coefficient differential equation. So instead of y prime equals lambda y, it's y double prime equals lambda y. And I'm going to specifically say lambda greater than 0, and we'll see why mathematically that's going to appear to be necessary in a minute. But it's rather disappointing to have this restriction. The first question that I have on the PDF is there something wrong or weird about this if we think of it as a special case of this guy? Well, you bet, because that becomes negative. That's supposed to be the spring constant. This was supposed to be a positive number. This would make the spring constant negative. It would mean if you pull the spring out away from its equilibrium position, you stretch it this way, the force is going to make it go further. It's going to blow up. So we would expect right away that this is not a restoring force. This is some sort of positive feedback that's going to make the system blow up. Not very physically reasonable in most situations. Okay, and that'll actually be confirmed when we look at the mathematics that it's going to be something that blows up, that's not bounded, things like that. Okay, but it turns out we're going to see in a minute why I would make this weird restriction that's unphysical. Okay, so I claim we can just flat out guess two solutions that are not multiples of each other, to use a little more sophisticated terminology, two linearly independent solutions of this equation, just based on what we were doing in problem 1. In problem 1, we saw something where if you take one derivative, you get the same function with a constant coming out. Here we want two derivatives. Okay, so to be really explicit, let's say if it was y double prime equals 4y, well, what if we had a function when you differentiated it, it was twice itself? Then when you differentiate it twice, you'll get 4 times itself. Well, of course, we know what would work there. Y equals some constant times e to the 2t. And now wait a minute. Is this the only number that squares to 4? Oh, plus or minus. So in general, it's going to be y double prime. Sorry, it's going to be y of t. The solution is going to be, one of them is going to be root lambda times t, and e to the minus root lambda times t. Okay, and now you can see why I would make this stipulation. If we've never heard of a complex number, and you haven't, trust me, right? We're pretending we've never heard of imaginary complex numbers. We wouldn't be able to do this right here. It just would not work. Okay, and of course that's a big hint as to what's going to happen when we remove this restriction. Okay, but it's very instructive to go through this case carefully to really make sure we understand this one, where we aren't forced to do complex numbers. Okay, now given these guys, okay, we can do the same trick, but a bit more complicated and wonderful version of the same trick. Before, we could multiply this by a constant, because this is a linear equation. Both sides get multiplied by the same constant, and this is still a solution. Well, but I could multiply this by a different constant, and then the really cool thing is, let's see if I can just erase that, I can add them together. And it's easy to see that if I add them together on the left-hand side, because the derivative of a sum is the sum of the derivatives, that's really important. And because this is just multiplication by a constant, by some fixed quantity, then this is going to be a solution as well. That's the linearity principle, mathematicians' terminology, or the superposition principle, physicists' terminology. Really important. And it's not true for all physical systems by any means, but when it is true, it's wonderful. Okay, so that's the answer to C. Can we make something a more complicated solution just out of these building blocks? And of course we can, and it's wonderful. But it's really because of the linearity. Okay, so alright, so what that allows us to do, hey, we've got two we've got two undetermined constants. That should match two initial conditions, as I was mentioning before, maybe in the first video. Okay, let me get a clean sheet. I really need to switch back to my whiteboard method here because it's wasting paper, sorry. Okay, so let's look at, for example, here's a problem we could do. This is part D in the PDF. Let's solve this problem. Lambda is still positive, and I'm going to cherry pick a little bit. A little kind of a weird problem. Initial value position is 1, and initial velocity is root lambda. Okay. That's obviously not, it should look contrived, and it is contrived. It's to get an easy solution. Okay, well, let's just look here, just by inspection. Okay, here's why. If I set C1, well, make sure you pause it here. You really should do this yourselves, right? But here's the answer. It's a pretty easy answer. If you set C1 equals 1 and C2 equals 0, you're certainly going to get 1 for y of 0. And then when you take the derivative, the root lambda is going to come down, and you're going to get root lambda. Okay, so there is a particular kind of contrived initial condition where y of t is just plain e to the root lambda t. Boom. Okay, the main thing is I just want to look at some of the important solutions to this and analyze them qualitatively. It's really important. Okay, so that's just exponential growth. Okay, and it really is growth because this really is positive. Okay, and that's of course because this guy is going upward right here. The slope is positive, and it continues to be positive everywhere. So, questions. Does this have any critical points? No critical points. Interesting observation, and it's going to be very interesting later on. Okay, so I don't know if you want to consider that good or bad, but it's a very important thing to know about a function, whether it has a bunch of wiggles, ups and downs, maxes and mins, critical points, or none. It has none. Okay, is it bounded? I shouldn't abbreviate that. Sorry. Is it bounded? Well, in one direction only. Because, this is the same function we were analyzing in number 1, isn't it? Okay. And is there a simpler relation between y of t1, y of t2, and y of t1 plus t2? These all have the same answers as before. Yes. It's an exponential, so it has the wonderful multiplicative law for exponents. Okay. So, what about if we did, we'll go through really quickly through the next one. E, just ask the same thing for initial condition y equals 0 equals 1, y prime of 0 equals negative root lambda. Oh, well, guess what? That's a decaying exponential. This isn't seeming that different from problem 1. It's like, oh, okay, yeah. It's just that in this case, the very same lambda had the increasing solution and the decreasing solution. There is a big difference there. That here, this was a solution for a certain lambda. This was a solution for the opposite lambda. They couldn't be solutions to the same equation. Here, these are different behaviors you get from the same equation. But, okay, again, no critical points. It's not bounded, although it's bounded in one direction. That's not so great. And, of course, it's an exponential, so we have a nice relationship between with the y of t1 plus t2. Okay. Now, these were really contrived problems. We really should be solving these. I claim we really should solve these two problems. One is y of 0 equals 1, y prime of 0 equals 0, and then when you switch the 1 and the 0. Because then, if I give you y of 0 equals 5 and y prime of 0 equals 3, I can just take 5 of this problem plus 3 of the switched problem, and it's easy to show that you get a solution to the general problem. So this is what would be called like a basis solution with the simplest non-zero initial condition. Pure motion, or pure position information, no motion, then the 0, 1 would be pure motion, not no position, starting from the equilibrium position, if it's a physical system. Okay. Now, this guy is a little bit less familiar, okay, but it's still really cool. So here, we can just do a little bit of work here. The general solution was e to the root lambda t with a c1 in front, e to the minus root lambda t. We're going to have to write down y prime of t. So that's root lambda c1, e to the root lambda t, so minus root lambda c2, e to the minus root lambda t. And then the great thing is I'm plugging in 0 everywhere here. Okay, so if this is when I plug in t equals 0, I'm going to get c1 plus c2, and that's supposed to be 1. And this whole thing is root lambda times c1 minus c2, and that's supposed to be 0. Well, luckily the root lambda cancels out. This says c1 equals c2, therefore they're both equal to a half. Okay, so c1 equals c2 equals 1/2. Okay, now, whether the next thing I'm going to write down is familiar to you depends on whether you've seen hyperbolic trig functions before. And if you haven't, then here's a very, very brief introduction to them, because it's not going to be my main focus. What we've got is that y of t, the solution, is e to the root lambda t plus e to the minus root lambda t all over 2. That's called the hyperbolic cosine of root lambda t. If you want the definition of just cosh with nothing in it, just set lambda equal 1. Okay. So what does this look like? Well, it's a nice combination. It's just half of this plus half of this. Okay. And so the e to the lambda t blows up in the positive direction. The e to the minus root lambda t blows up in the negative direction. It's an even function because if I switch t to minus t, these just switch and nothing happens. Okay. And at 1, at 0, t equals 0, of course, by definition, by fiat, we wanted that to be 1, and we wanted the derivative to be 0. Okay, so it's something that's exponential growth in both directions symmetrically. You might wonder, if you've never seen this, what does this have to do with hyperbolas? That's where the h's come from. And what the heck does it have to do with cosines? Well, we'll see what it has to do with cosines, or at least one of the big relationships pretty soon. Okay, the hyperbola stuff, that's for another video, and I've made other videos about that. Well, what about the pure motion example? We'll do that, and then we'll be pretty much done with this part. Okay, so y of 0 equals 0, y prime of 0. Oh, let's see, what were the other qualitative questions? This is not bounded in either direction. It does have one critical point, but it's not like it's turning around over and over again, like a certain function without the h might be doing. We'll see that soon. And, oh yeah, and does it have a nice relationship? Well, cosh of t1, let's just set lambda equal 1 for a second. Cosh of t2 and cosh of t1 plus t2. Well, if you are familiar with hyperbolic trig functions, you know that this might strike a chord that there's maybe something going on here, but it's not simply, definitely not simply that this is this times this. And it's, in fact, this you don't even express just purely in terms of these two coshes, even with a more complicated expression. If you haven't seen it, it's a good thing to look up. Let me tell you that. Okay, look up hyperbolic functions, look at the sum rule. It might look somewhat familiar. So, again, these are all teases for how we're going to compare to the key case we're looking for, which is where we make this lambda negative, because we know that this is still working on stuff like, oh yeah, now we can still see, hey, things are blowing up. This is not what oscillating springs do. Okay, so let's do, let's just set this equal to 1. I think it's slightly different from how I had it in the PDF. So this is pure motion initial condition. If this were a spring, some sort of weird, bizarre, negative spring, positive feedback kind of spring, we put it at the equilibrium position, we give it a push. Okay, so now we already had y of t and y prime of t. There we are. Okay, and when we set t equals 0, we get a c1 plus c2 equals 0, and c1 minus c2, oh yeah, all times root lambda equals 1. Okay, and so c1 and c2 are opposite of each other. Okay, and so it's pretty easy to see c1 equals minus 1 over 2 root lambda, and c2 is, no, that's plus. c1 is minus 1 over 2 root lambda. Hey, my handwriting is just going downhill. It's late at night. Okay. So let's summarize it with a little bit better handwriting. And I keep marking up. No, that's the same page, thank goodness. Okay. I'm trying to do it so I keep marking up just the same piece of paper over and over again with the bleed through. So we get y of t. I'm going to put out the 1 over root lambda in front because it's not in the official definition of what's called the hyperbolic sine function. That's what we get. And that's 1 over root lambda times the hyperbolic sine of root lambda t. Okay. Again, you don't have to know anything about this guy, but it helps. It probably helps if you know some about it. The one thing I'll do is I'll just graph it. Good exercise, or a good thing to look up. Ooh, not quite like that. It's like that. It's not flat here. It's not got a critical point here. It's exponential negative blow up here. That's this guy. Exponential positive blow up here. As t goes to infinity, that's this guy. It's an odd function because when you switch t to minus t, these guys switch roles. And so what's qualitatively going on here? Okay, certainly absolutely nothing like oscillations. Okay, we're mathematically, hopefully, working up towards the real case we care about. But qualitatively, physically, it just seems like we're nowhere near. Um, because this doesn't have any critical points. Oscillations, would go like this, suggestive curve maybe, and this doesn't look like that. So it's kind of weird that we're getting closer and closer to the system that we think we should be solving, and yet it's not at all obvious that we're getting close in terms of the solution we get. Okay, um, and then another feature again is we seem to have lost this wonderful relationship. When we stuck to pure exponentials, let me say just a word about that, and this is getting kind of long. When we stuck to pure exponentials as the solutions, like this guy, that is an exponential that has a wonderful relationship between y of t1, y of t2, and y of t1 plus t2. But it was a contrived initial condition. It'd be really wonderful if the solutions with the really natural initial condition, like this pure velocity condition or the pure position condition, had some really nice similar relationship. And it just doesn't. Okay? And we're going to see an echo of that with the oscillation story as well. Okay.